In the world we live in, everything around us, from a leaf, a speck of dust, a human being, to the stars, is made of tiny particles of matter. But how did we come to know this? What led humanity from knowing nothing about atoms to building atomic bombs, particle accelerators, and even mapping the microscopic world? The answer didn't come from a stroke of luck. It's the result of centuries of inquiry, skepticism, experimentation, and quite literally, smashing the material world. From the moment humans asked, "What lies inside matter?" we began an endless journey peeling back the layers of the universe, like an infinite onion. More than 2,500 years ago, long before microscopes or laboratories existed, ancient Greek philosophers proposed a bold idea. Matter is made of tiny, indivisible particles, called atomos, atoms. But this wasn't science. It was philosophy, since they had no way to prove their claims. It wasn't until the early 19th century that John Dalton, an English chemistry teacher, laid the foundation for modern atomic theory through observations and experiments. Dalton suggested that each element is made of atoms identical in mass and properties, and that in chemical reactions, atoms aren't destroyed, they merely rearrange. This was a remarkably advanced view. However, Dalton wasn't the first to come up with such ideas. William Higgins, another chemist, had published similar ideas on elements and anti-elements years earlier. He accused Dalton of idea plagiarism. But history remembers not only those who had ideas first, but those who systematized them, proved them through experimentation, and laid foundations for future advances. Dalton did just that. From then on, atoms were no longer just philosophical hypotheses. They became scientific subjects that could be tested, measured, and refined. But a big question remained. If the atom is the fundamental particle, can it be split further? One man did just that. He discovered the electron. Nuclear physics and quantum mechanics fields that once seemed distant are now central to all modern technologies. To build the smartphone you're holding, scientists had to smash atoms together millions of times per second. In part 2 of the Great March of Science, we'll step back and follow this extraordinary journey, from ancient atomic theory to the discoveries of the proton, neutron, quantum models, and the even smaller particles inside matter. The cathode ray experiment and the birth of the electron. At the end of the 19th century, as scientists sought to understand atoms more deeply, a groundbreaking experiment emerged, the cathode ray experiment by British physicist Joseph John Thomson. This experiment not only revolutionized the atomic model, but also led to the discovery of one of the most fundamental particles, the electron. Thomson used a vacuum glass tube fitted with 2 electrodes connected to a high-voltage power supply. When the voltage was applied, a faint beam of light, called a cathode ray, emerged from the negative electrode, cathode, and moved toward the positive electrode. But was this just light or something more tangible? To find out, Thomson applied electric and magnetic fields to the cathode ray. The results were astonishing. The beam deflected toward the positively charged plate. This indicated that the cathode ray carried a negative charge. It was composed of smaller particles. These particles were electrons. By measuring the charge-to-mass ratio, EM, Thomson discovered that the electron's mass was extremely small, more than 1,800 times lighter than a hydrogen atom, the lightest known atom. This meant the atom was not indivisible, as once thought, but was made up of even smaller components. The plum pudding model. Following his discovery, Thomson proposed a simple atomic model. A positively charged sphere with negatively charged electrons embedded within it, like raisins in a pudding. This became known as the plum pudding model. Though simplistic, Thomson's model was a huge leap forward. It suggested that atoms weren't solid, featureless spheres, but systems with internal structure. For this groundbreaking work, Thomson received the Nobel Prize in Physics in 1906. He also mentored a generation of future Nobel laureates, including Ernest Rutherford and Niels Bohr. However, The plum pudding model soon revealed its weaknesses. It couldn't explain the true structure of atoms, something that one of Thomson's most brilliant students would soon uncover. Rutherford's gold foil experiment, a revolutionary insight. Ernest Rutherford, one of Thomson's most outstanding students, did not fully accept the plum pudding model. With sharp intuition and independent thinking, he questioned whether negatively charged electrons could truly float randomly within a positive sphere. To test this hypothesis, he devised a groundbreaking experiment. From 1909 to 1911, Rutherford, along with his colleagues Hans Geiger and Ernest Marsden, conducted a now classic experiment, firing alpha particles, positively charged, at an ultra-thin sheet of gold foil, just a few micrometers thick. The results were astonishing. 99% of the alpha particles passed straight through the foil unaffected, but a small number were deflected, and a few even bounced straight back. This was completely at odds with the plum pudding model. If positive charge was evenly spread out, there would be no reason for alpha particles to be repelled so strongly. Rutherford famously exclaimed, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." A new atomic model. From these results, Rutherford concluded that the atom is mostly empty space, with its positive charge and mass concentrated in a tiny central region, the nucleus. Electrons orbit this nucleus, similar to how planets revolve around the sun. This model, known as the planetary model of the atom, completely replaced the plum pudding model and laid the foundation for future discoveries in atomic structure. For this monumental contribution, Rutherford was awarded the Nobel Prize in Chemistry in 1908 and became known as the father of nuclear physics. In his honor, the element Rutherfordium, a ref on the periodic table, bears his name, a fitting tribute. The Bohr model and the quantum leap. After Rutherford established the nucleus-centric model with orbiting electrons, a crucial question arose. Why don't the electrons spiral into the nucleus under the pull of opposite charges? According to classical physics, a charged particle in circular motion should continuously emit electromagnetic radiation and lose energy, leading to an inevitable collapse into the nucleus. But in reality, atoms are stable. Why? In 1913, Danish physicist Niels Bohr, Rutherford's student, offered a bold solution by blending classical mechanics with Max Planck's quantum ideas. Bohr proposed, electrons do not orbit the nucleus arbitrarily, but follow specific paths called stationary orbits. While in a stationary orbit, electrons do not emit energy. Electrons absorb or release energy only when jumping from one orbit to another in discrete packets called photons. This model successfully explained the line spectra of the hydrogen atom, a set of distinct wavelengths of light emitted when electrons transition between energy levels. It marked the first time an atomic model could explain experimental phenomena using the language of quantum mathematics. Limitations of the Bohr model. Despite its brilliance, the Bohr model had serious limitations. It only worked well for simple atoms like hydrogen or helium. For atoms with many electrons, the model became overly complex and failed to explain phenomena like energy sublevels, internuclear forces, or complex chemical bonding. Nonetheless, Bohr's contribution was immense. He brought quantum mechanics from theory into practice, paving the way for a scientific revolution the world had never seen before. Proton, the first particle. In 1917, Rutherford conducted a series of experiments in which he fired alpha particles at nitrogen gas. The result was surprising. The collision produced oxygen and a positively charged particle with a mass equal to that of a hydrogen atom. Rutherford named this particle the proton, from the Greek word protos, meaning first. This was the first time humanity realized that the nucleus itself was made of smaller particles. Neutron, the missing piece. Yet one puzzle remained. If the nucleus only contained protons, why didn't it break apart due to the strong electrostatic repulsion between the positively charged particles? The answer came in 1932, when physicist James Chadwick carried out a series of intricate experiments by bombarding beryllium with alpha particles. The result was a new kind of radiation uncharged, yet capable of knocking protons out of paraffin wax. This revealed the existence of a neutral particle with a mass nearly equal to that of the proton. Chadwick named it the neutron. This discovery solved several mysteries. Neutrons stabilize the nucleus by offsetting the repulsive forces between protons. They allow the existence of heavy atomic nuclei such as gold or uranium. Because neutrons are unaffected by electromagnetic forces, they became ideal tools for probing deep into atomic structures. For this groundbreaking work, Chadwick received the Nobel Prize in Physics in 1935. Humanity now had the three fundamental components of the atom: electrons, protons, and neutrons. The nuclear force and the liquid drop model. Even with this knowledge, a question lingered. How are protons and neutrons bound so tightly within the nucleus, despite the Coulomb repulsion between positively charged protons? In 1936, Niels Bohr and John Wheeler proposed the liquid drop model to describe the nucleus. They likened the nucleus to a droplet of liquid, where nucleons, protons, and neutrons are held together by a powerful nuclear force, while also being subjected to surface tension-like repulsive forces. In 1935, Japanese physicist Hideki Yukawa proposed that this strong nuclear force was due to the exchange of intermediate particles called mesons. His theoretical insight was a major step in understanding intranuclear interactions. Yukawa received the Nobel Prize in 1949 for his contribution: nuclear reactions and atomic energy. When a neutron strikes a uranium atom, the nucleus may split into two smaller nuclei, releasing enormous energy. This process, known as nuclear fission, became the basis for both nuclear reactors and atomic bombs. Between 1942 and 1945, the Manhattan Project in the United States utilized this principle to develop nuclear weapons, marking the first time humans had turned nuclear theory into tools of mass destruction. From then on, atomic power became a symbol of both scientific progress and global peril. Looking deeper, quarks, gluons, and the Standard Model. Just when scientists thought protons and neutrons were fundamental particles, the 1960s brought a new surprise. Physicists Murray Gell-Mann and George Zweig proposed that protons and neutrons were themselves made of even smaller particles called quarks, held together by force-carrying particles called gluons. This theory, along with the discovery of the Higgs field, the weak force, and the unification of electromagnetic and weak interactions, formed the Standard Model of particle physics. This is the most advanced theoretical framework we have today to explain the fundamental particles and forces in the universe. Conclusion: a universe within. Would you like me to write a literary-style conclusion, like in part 1 of the series, emotional, evocative, and story-driven? Here's one possible ending. When we gaze at the night sky, we see stars. But when we look down into a speck of dust, an atom, or an electron, we see an entire universe. From the quiet experiments in Joseph Thomson's dark lab to the violent collisions inside modern particle accelerators, humanity has ceaselessly broken apart matter in search of truth. Each shattered fragment, smaller than a billionth of a millimeter, has opened new chapters in science's grand epic. We once thought the atom was indivisible. Then came the proton, the neutron, and later still, the quark and the gluon. What lies beyond them? Could there be something inside quarks? And if so, when will we have the courage, the energy, and the humility to find it? Perhaps the beauty doesn't lie in the answers, but in the longing to seek. Inside every measurement, every reaction, every dry mathematical equation, lies the spark of human curiosity, the soul asking, what is this universe, and what does my existence mean within it? In World War II, atomic energy made the world tremble with fear. But today, our understanding of nuclear and quantum science fuels medicine, clean energy, and billions of devices shaping modern life. From a speck of dust, we can create light. From an idea, we can change humanity. Science is not a destination,